we will prove this. Pn is equals to 1 plus 2 plus 3 up to n is equals to n into n plus 1 upon 2 for all n is greater than 1. In earlier we have proved that this is equal to this, but now we will prove by mathematical induction. So, given statement that is Pn is equals to 1 plus 2 plus 3 up to n is equals to n into n plus 1 upon 2. Now, our first step is for n is equals to 1. Then Pn is equals to 1 is equals to, we have to prove this side also to 1 plus 1 upon 2, this is 1. So Pn is or P1 is true. Our next step is inductive step. In this we have to put let Pk be true for some positive integer. Now we have put Pk be true. We are assuming that Pk is some positive integer. Then this is the Pn. So we will put Pk is equals to 1 plus 2 plus 3 up to n or up to k, because we are putting P is equals to k, then up to k is equals to k into k plus 1 upon 2. This is our equation 1. We have put the value Pk is equals to 1 plus 2 plus 3 up to k, which is equals to k plus 1 upon 2. Now we shall prove that P k plus 1 is also true. We have to prove that P k plus 1 is also true. Then P k plus 1 is equals to 1 plus 2 plus 3 up to k, and k plus 1 is equals to k plus 1 k up to k plus 1. Pk is equals to 1 plus 2 plus 3 up to k plus 1. Now we know that up to k, from first equation we can write k plus 1 upon 2. So Pk plus 1 will be equals to k into k plus 1 upon 2, and the remaining, which is k plus 1. Taking k plus 1 common, we get k upon 2 plus 1. Now we get k plus 1 k plus 2 upon 2, and which is similar to what we have put in Pk. In Pk we we have put k is equals to k plus 1 upon 2, that is our equation number first, and in this equation we get k plus 1, k plus 2 upon 2. Now we have to make in the form of like this. So k plus 1, and in k plus 2 we can write k plus 1 plus 1 upon 2, where k plus 1, if we assume k plus 1 is n, then k plus 1 is n plus 1 by 2. So this is proved. So now we can say that if pk is true, then pk plus 1 is also true. If pk plus 1 is true, whenever pk is true. After this we can write, hence by principle of mathematical induction, it is true that Pn is equals to 1 plus 2 plus 3 up to n is equals to n plus 1 upon 2 for all natural numbers which is greater than 1. This is our first example. Now we will see another. Now our second example is 1 plus 3 plus 5 up to 2 and minus 1 is equals to n square. Now Pn is equals to 1 plus 3 plus 5 up to 2 and minus 1 is equals to n square. This we can write. Now for n is equals to 1, P1 is equals to 1, and here 1 square is equals to 1, that is P1 is true. We can say P1 is true. If let Pk is true for some positive integer, we consider if pk is true where k is some that is k. Let pk is true for some positive integer k. Now we can put pk is equals to 1 plus 2 plus 3 up to 2k minus 1 is equals to k square. That is our equation number 1. Now we shall prove that pk plus 1 is true whenever pk is true. That pk plus 1 is equals to 1 plus 2 plus 3 up to 2k minus 1 plus 2k plus 1 is equals to, we can write pk plus 1 is equals to k square plus 2k square, because from here we can see that this is the value of k square from equation 1, and 2k plus 1, k square plus 2k plus 1, we can write k square plus 2k plus 1, which is the square of k plus 1, which is similar to the given equation, that is n square So we can say that p k plus 1 is true whenever p. Now students, if you have any problem, any doubt or any clarification, you can ask to me or you can message to me, or please complete your copy of what